Hello, this is a lecture that will cover the scientific revolution. What you're looking at here is sort of the beginning of what the understanding of the solar system was. The scientific revolution is going to be about 150 years of huge scientific advancements. There are two major changes that happened during this time. The first major change is the change from geocentrism to heliocentrism. The second major change is the change in the understanding of the shape of the planet's orbits. At first, people thought the planets orbited in circular motion, and later it is discovered that in fact they orbit in an elliptical pattern. So to get us started trying to understand these two major changes, I am taking us way back to 310 BCE. This is to show you that there was a very early Greek philosopher. His name is Aristarchus, and he actually had this idea of the heliocentric model of the universe. Heliocentric, helio means sun, centric is center. So what Aristarchus actually came up with in 300 BC is that the sun is here in the center, and that the earth and the moon are orbiting the sun. Now, way back then, nobody believed Aristarchus, and his theory actually was lost to history for several years. There's a couple main reasons why no one believed Aristarchus. The first thing is because people can go outside and they can watch the sun move across the sky. So to our eyes, it seems to be true that we are still and it's the sun that's moving. The other reason why people didn't believe Aristarchus is because he was proposing that the earth was in motion, and people said, hey, well, if the earth is moving, wouldn't we feel it? Wouldn't we feel the ground shaking under our feet? So for this reason, his theory, his model was never accepted. Instead, what people chose to accept was a model by Aristotle. Now, this is an illustration of what the Aristotle's model would have looked like. Aristotle believed in geocentrism, geo meaning rock, the earth being in the center. And what Aristotle believed was that the earth was surrounded by these crystalline spheres, or like a glass case. And within that glass case, the moon was like a little marble that was rolling around in there in this glass case. And then that glass case was also encompassed in another glass case. Venus was in that one, the sun, Mars, etc. So you can kind of think of this model almost like the Russian nesting dolls, where each of these planets had their own glass case, and they were locked in this glass case. They could roll around in there, and they were all orbiting the Earth. Well, about 1,000 years later, after Aristotle came up with this model and people accepted it, the calendar started to become off, and this became a big problem. So after the Romans had accepted Christianity, a Roman emperor asked this guy here, an astronomer named Ptolemy, to fix the calendar. What's wrong with this calendar? We have to fix the calendar. Again, Aristotle's model was holding because people believed that, hey, our senses, this model makes sense to our eyes. This model makes sense to our sense of touch, right? We don't feel the earth moving. We don't see it seems like we see the sun orbiting us. The other reason why Aristotle's model held for so long was because the church adopted this model. So now the Catholic Church was teaching this model, which put Ptolemy in a really difficult spot. The emperor wanted him to fix the calendar, but he couldn't go against what the church was teaching. The reason why it was important that he didn't go against the church is because the church didn't want to be wrong on this. If the church was wrong about this, and that they would have to admit they were teaching something that was incorrect, and this might lead people to question, hey, what else is the church maybe not correct about? So Ptolemy uses Aristotle's model, and he adds to it. in order to try to make the calendar make sense. The big problem with the calendar was the motion of Mars. So every night in the night sky, you could look at Mars, and there are certain parts of the year where Mars, it looks like if you track it every night in the night sky, for about 2 weeks, it'll be going forward. It'll then seem to go backwards and then go forward again. This was really confusing for people. They didn't understand why this was happening. And when the calendar became off, important holy days like Easter and Christmas were not lining up with the season that they were traditionally celebrated in. So Easter wasn't happening in spring, Christmas wasn't happening in winter. They had to fix the calendar. To solve this problem, what Ptolemy did was he added a motion into the planets. So what he believed was that the planets fit in the crystalline sphere, like Aristotle had suggested, but that the planets would leave their orbit. So they would be orbiting. They're going to leave their orbit. They're going to do a circle and then join back up and continue on their orbit. He called this motion an epicycle. So if you ever read astrology and you've heard that Mercury is in retrograde or Mars is in retrograde, this is the motion that astrology is talking about. If you look at the planets in the night sky and you track their movements every day, at some point the planets are going to look like they're going backwards and then they'll appear to be going forward again. To solve the question of why they were doing this, Ptolemy came up with this idea of the epicycle. The epicycle is the loop-to-loop motion. The planet leaves its orbit, does a loop, and then rejoins its orbit. And this satisfied the Roman emperor, so this is the system that stayed in place for about 500 more years. That's going to bring us to the events of the scientific revolution. Now, I put all these on here. You do not have to remember all these dates, but I wanted to show you how things started and then how long it takes for them to come to the understanding, our sort of modern understanding of the solar system. It takes about 150 years for all of this progress to be made. And this guy, Copernicus, is largely credited with starting this scientific revolution. So this is Copernicus. He was a Polish astronomer, and he was being employed by the Pope, by the Catholic Church. Now, this is about 500 years after Ptolemy came up with his idea of the epicycles. And guess what? The calendar was off again. So now the Pope says to Copernicus, you're an astronomer. The church wants to pay you to try to figure out what's going on with the calendar so that we can make sure that the holy days are lining up with the right season. Copernicus does a lot of research, and he is going to find Aristarchus's original idea of heliocentric theory. So in researching the past, this is a Renaissance idea, right? You're going to go back and look at what the Greeks and Romans knew about the world. When Copernicus did this, he realizes, hey, someone else had proposed this idea of heliocentric theory. And he thinks, you know what, this heliocentric theory, it might be correct. But again, he's worried because this is against the teaching of the Catholic Church. So what he did was he wrote this book. It's called On the Revolutions of the Heavenly Bodies. And this is where he's going to be the first modern astronomer to propose heliocentric theory. He's not the first one who ever came up with it. That was Aristarchus. But Aristarchus doesn't get any credit. Copernicus gets the credit because he rediscovered the theory. But Copernicus was afraid to publish this. So he actually had his book prepared, and he waits until he's dying. On his deathbed, he gives his book to his assistant, and he says, publish this now. The first page of the book even included a letter to the Pope that said, hey, listen, Pope, I know that you wanted me to do this research in order to confirm geocentric theory, but what I found out was I don't think geocentric theory is right, even though that's what the church has been teaching. Copernicus dies and his book is released. Guess how the church reacts to this? they're really, really mad, right? They paid Copernicus to support their theory, and here he writes this whole book saying that their theory was in fact wrong. So what's the church going to do? If you remember from when we talked about the Baroque period and the Council of Trent, in the Council of Trent, the Catholic Church created a list of banned books. And so what the Catholic Church does at this point is they put Copernicus's book on the Revolution of the Heavenly Spheres on this list of banned books. There's a link right here if you're interested in all the books that were banned by the Catholic Church. You can click on that and you'll see a list. So Copernicus dies, his book gets banned, but when you think about information that is forbidden, this is something that doesn't stay hidden for long. Other astronomers and scientists like Galileo are going to hear about Copernicus's findings, and they're going to seek out his book and read it. When they read it, it's going to inspire them that, hey, you know what, this heliocentric theory might be true. So what Galileo does is that he is going to see a new invention, which is the telescope. Okay, he did not invent the telescope. The telescope was invented by someone else. What he did was he made the telescope more powerful. So if I ask you, for example, on a test, what was Galileo's contribution to the scientific revolution, please do not tell me that he invented the telescope, because he didn't. He made it more powerful. He used his new telescope to look at the moons that are around Jupiter. He looks at the moons around Jupiter first, and what he realizes is that the moons, after looking at them for several days, he realizes that they are orbiting Jupiter. So you might think about this and say, who cares? But this is actually really, really important, because what he's done here is he's proven that Aristotle's theory of all of the planets fitting in a crystalline sphere or a crystal glass case around the Earth, that can't be correct. The moons around Jupiter would be breaking that glass sphere. So he thinks about this, he observes, and then he uses logic and he says, hey, well, if these moons are in motion, maybe other things in the world are in motion. So then he starts looking at our moon, the Earth's moon, our beautiful moon. And he starts looking very closely with his high-powered telescope, high-powered at the time, and he notices the craters, the shadows that are on the surface of the moon. And he starts to come up with an idea about what those craters could be. He realizes that the moon must have mountainous peaks and deep valleys. And it is when light hits those mountains, the shadow from the mountain is passed down onto the surface of the moon. So when we look up at the moon and we see dark spots on it, that is because the mountainous peaks are blocking the light from hitting that area. So he observed that. Next thing he's going to do is he's going to reason about it. He's going to use logic and reason. Well, what light is it that could be hitting the moon? The only light in our solar system comes from the sun. So he says, hey, the sun's light must be hitting the moon. Now, if any of you have gone out and looked at the moon, you will know that sometimes we have a full moon, sometimes we have a partial moon, sometimes we have just a little sliver of the moon. And you could notice that the moon is blocked. It almost looks like it's blocked by something, right? The light that is illuminating the moon is sometimes not showing the whole moon. And from this observation, Galileo reasons that the Earth must be in between the sun and the moon. If the Earth is in between the sun and the moon, then it is the Earth's shadow that is blocking the light on that part of the moon when we see a little crescent moon. And this proves heliocentric theory. So Galileo's big contribution to the scientific revolution is that he proves heliocentric theory. Galileo was a really cool guy, and he does lots of other stuff as well, so I hope you'll do a little research on him. One of the things that made him so cool is that he wrote in Italian vernacular. Now, this book you see here is Galileo's book. It's called the Dialogo, and it was different than Copernicus's book. Copernicus wrote in Latin, because Latin was the language of the scholars, meaning that people who had been trained in universities would have had to learn Latin. And then when they wrote this scientific information or treatise, they would write it in Latin. So it was kind of a way of keeping the knowledge among only a few people. If you didn't read Latin, you couldn't read this book. Galileo could read Latin, but he chose to write in Italian. This is the common language of the people because he wanted everybody to be able to know this information. Galileo was also hired by the church, so this shows that the church really did support scientists. However, Galileo, like Copernicus, was hired to help prove and support the church's stance that geocentric theory was correct and heliocentric theory was incorrect. But, of course, I just got done explaining that Galileo proved that heliocentric theory was in fact correct. What Galileo does next in this book, Dialogo, is what gets him in big trouble. So what he did was he wrote this story, the dialogue. And the dialogue had three characters. You had one character who believed in geocentric theory. Galileo chose to name this character Simplicio. This word Simplicio sounds a lot like our word for simple or simpleton, meaning this character was a dummy. The person who believed in geocentric theory was a dummy. He named another character Savante. Savante believed in heliocentric theory. Has anyone ever heard of a savant? This is like a genius, a really wise person. So the person that believed in heliocentric theory in Galileo's story was the wise person. And then his third character was kind of neutral, and he was listening to the argument from both of these gentlemen. Now, if you were the Catholic Church, how would you respond to this? Galileo is really poking the bear here, right? Not only is he saying, hey, geocentric theory is wrong and heliocentric theory is right, he's saying, you're stupid if you believe geocentric theory. So what happens next is the church is going to ban Galileo's book, but that's not all. This is the time of the Inquisition. And for anybody who has never learned about the Inquisition, this is a movement where many people were accused of being heretics or of being Jewish, and they were brought before a board of inquisitors where they were questioned. The inquisitors would either decide, yes, you are innocent, or no, you're guilty, but they would torture people in order to come up with this verdict. And then they would either decide to kill the person or set them free. So now Galileo was up against this board of inquisitors, and this is a place you do not want to be. But luckily for Galileo, he was 68 years old at the time, and this was considered an old man. And the board of inquisitors thought, hey, this is going to look really bad if we torture an old man. So he did not get tortured, but instead he was sentenced to life in prison, and he was held under house arrest. So he is able to stay at his home in Florence, and he's going to continue to do scientific experiments from his home, which is really lucky. But the church does excommunicate him. So remember, excommunication is the worst punishment the church can give you. It means that he is not allowed to go to heaven, and he will go straight to hell. There's no chance of forgiveness. Here is an interesting story. It takes the church until 1992, 359 years after Galileo's death, to actually clear him of any wrongdoing. That's how mad the church was. They waited 359 years to pardon him. So if you are Catholic and you believe what they are teaching, it would mean that Galileo was roasted in hell for 359 years before one day the Vatican, which is the home of the Pope, writes this speech, and they say that what happened between the church and Galileo was a tragic mutual incomprehension. So even after 359 years, that's not much of an apology. It really sounds like, hey, we were both wrong, but we're going to go ahead and lift Galileo's excommunication so that he could then go up to heaven. So we have Copernicus, the first modern scientist to propose heliocentric theory, Galileo, who confirms heliocentric theory. He proves it's correct. Next, we're going to look at a German astronomer named Johann Kepler. Kepler was planning to be a minister, and he was a very devout religious man, but he also was a mathematician. So he started coming up with different plans for the solar system. At first, because he was very religious, he tried to make geocentrism work, and all of his mathematical equations to solve this problem of the epicycles that people have been struggling with since the time of Ptolemy, they were not working. So what he does is he lowers himself to become an assistant to another astronomer. This guy is called Tycho Brahe. Tycho Brahe was a Danish astronomer, but he had this very fancy observatory that was built for him by the Duke of Prague. And so he was living there in Prague, making lots and lots of observations of the night sky. This data was collected over years. Both Brahe and his sister were astronomers, and they worked on this data. When Kepler arrived, these two really butted heads. Kepler was religious and devout and really wanted to get his hands on Brahe's data. Brahe, however, was not so interested in sharing. Brahe was kind of a wild guy. If you look at this picture, you might notice his nose looks a little weird. That's because his nose was cut during a fight. So someone sliced off the end of his nose, and he actually would wear a little metal cap over his nose. He was known for drinking and partying. So these two, they were opposites. But they prove a really important part of this scientific method that's going to be so important moving forward. And that is that these discoveries can take place when two things come together. Observation, which is what Brahe was doing, and reasoning, applying logic to try to solve these problems. Eventually, poor Brahe, he ended up having a ruptured bladder, and he dies of an infection. So he's laying in bed for several days. He knows he's about to die, and he calls in Kepler. He says, go ahead, take my data, use it so that all of my work is not in vain. After Kepler gets his hands on the data, now he's able to use his math skills and start solving this problem of the epicycles. Kepler believed that God actually used geometry to create the universe, and so he believed that in figuring out the math that answered these questions about the universe, he was like reading the mind of God. And because of this data, he was able to come up with his 3 laws of planetary motion. Now, these are really incredible. They're a little hard to understand, so I'm going to put them in kind of simple terms for you. The first law is pretty easy. Planets describe elliptical orbits about the sun, with the sun located at one of the foci of the ellipse. What this means is that Kepler realized with his mathematical equations that the planets don't travel in circular patterns, but that they in fact travel in elliptical patterns, and the sun is at one end of that ellipse. An ellipse is kind of like an oval. His second law is the law, it says the radius vector sweeps equal areas in equal times. With this law, he's able to figure out the speed of the planets. So now he knows the shape. His second law tells us the speed. And what he finds out is that the planets actually speed up when they get closer to the sun, and then they slow down when they're on the part of the ellipse that's further from the sun. Finally, his third law, now this one is tricky. The square of the period of revolution of a planet is proportional to the cube of its semi-major axis. Now, I'm not much of a scientist, so that sounds like gibberish to me, but I do know what that means. What Kepler figured out was that each planet gets slower in their orbit the further away they are from the sun. And this is actually what solves that problem of the epicycles. The reason why Mars looks like it goes backwards is because the Earth speeds up. There's a time period where the Earth is traveling close to the sun, so the Earth's speed of orbit is going to go faster than Mars. Because we speed up, it looks to us like Mars is going backwards. This is the same thing that happens, for example, if you're driving down the beach line and you get passed by a truck going 90, or let's say you are the fast car, right? Because if we're the Earth in this scenario, you would be the fast car. So let's say you're on the beach line, you're driving 90, and you're speeding past a truck in the middle lane that's driving 70. For the few moments that you're passing that truck, it's actually going to appear to be going backwards. Has anyone ever noticed this phenomenon? Yeah, it really happens. And then once you get far enough away and you look in your rear view mirror, then the truck is going to start seeming like it's going forward to you again. This is the same thing that happens with Earth and Mars, and that's what Kepler's third law was able to figure out. This is going to change the way people think about everything. People are going to start to think, wow, if Kepler could figure out the shape, the speed, and the path of the planet's orbits, what else can we figure out about the world? This idea that God used geometry to create the world is going to lead to what becomes known as a mechanized worldview. A mechanized worldview means that people thought that the universe, the solar system, worked like a machine, mechanized, mechanic, meaning that there was order to it. It was predictable. It was logical. It's a worldview, meaning that they applied that way of thinking not just to the solar system, but to lots of other parts of nature, including the human body. This is the first time we started understanding the human body as a machine. We have different systems that do different things, right? The pulmonary system is responsible for breathing. The circulatory system is responsible for moving the nutrients around. The cardiac system for beating the heart. All of these different things work like machines. With this knowledge, this is going to hugely advance not just our understanding of the solar system, but our understanding of many, many things. Because if you think about the world as a machine, then you realize that machines can be fixed. If you understand how they work, you can fix them, you can predict them, right? This is how we end up being able to predict the weather. NASA still today uses this technology to predict when is the best time to launch rockets. So this is really a huge change in the way people think about the world. It also leads to this idea of deism. Deism is spelled D-E-I-S-M, and a deity is a god. So what deism means is that people start to think that God created the universe, but he has no part in the day-to-day running of things. This was a way more scientific way of thinking about the solar system and the universe than what people held before, which was that all storms, all sicknesses were an act of God. God was punishing people or God was blessing people. When people start to think of the world through this idea of deism, they think, well, God just created the world, but God's not down there changing things day to day, sending plagues to make some people suffer, sending rainbows to bless other people. This is a completely new way of thinking about the world. That's going to bring us to our last scientist that is a huge part of the scientific revolution. And this guy is Isaac Newton. In fact, we know him best as Sir Isaac Newton. And this goes to show you how far the world has come in these 100 or so years. Where Copernicus hid his findings until after he was dead, Isaac Newton actually is going to be knighted by the king while he's still alive. So he becomes famous within his lifetime for his scientific discoveries, which means that the world went from not accepting these things to celebrating these things. Most of you have probably heard of the famous story of Newton's big discovery. He was able to discover the thing that Kepler was not, which is what holds the planets in their orbit. What keeps the planets from just spinning out into outer space? Isaac Newton came up with this idea when he comes up with his laws of motion and gravity. Very famously, the story was that a plague was hitting England, and Newton came from a wealthy family. If you had money during times of plague, you would get the heck out of town. So Newton was sent to his country house where he was sitting in the garden thinking about science. While he was sitting in the garden, he observed an apple fall from a tree. And he started reasoning. He thought about it. And he said, gee, maybe the same thing that pulls the apple to the earth actually pulls the moon to the earth. And this is gravity. The idea that the moon stays close to the earth is because the earth is larger than the moon. And so the earth's gravity pulls the moon towards it. The reason why the earth stays close to the sun and doesn't spin off into the solar system is because the sun is larger than the earth, and so it pulls the earth towards it. He wrote out his laws in his book, Principia. Now, unlike Galileo, he's going to write Principia in Latin, right? So he's continuing this idea that Latin is the language of the scholars. You don't need to know these mathematical equations. I just want you to know his contribution, which was that he discovered the force that held the planets in their orbits.